Welcome to the 101 TiDB Technical Essentials course. This is Module 1, TiDB Database Architecture Overview. My name is Jeff and I am your instructor for this module. After completing this module, you will understand the overall architecture of TiDB Database and describe the main features of TiDB Server, TiKV, and the PD. Before we get started, there's something you need to know. When we say TiDB, we can mean one of two things. The first is the database itself. It's called TiDB. Second, there is a TiDB component within the TiDB database. Once you understand this, it shouldn't cause a problem. Let's move on to TiDB architecture. TiDB is a distributed relational database that supports both online transaction processing and online analytical processing. Databases that support both OLTP and OLAP use cases are also known as Hybrid Transactional Analytical Databases, or HTAP databases. TiDB has horizontal scale-out and scale-in, financial-grade high availability, real-time HTAP, and cloud-native distributed support. In addition, TiDB is compatible with the MySQL 5.7 client protocol, and it is compatible with the MySQL ecosystem. The three components of the TiDB database are PD cluster, TiDB server, and TiKV. The PD cluster is the control center of the entire database. Think of it as the brains of TiDB database. It is responsible for generating global timestamp oracle timestamps, scheduling the distribution of regions in TiKV nodes, collecting the health and distribution status of TiKV nodes, and assigning transaction IDs to distributed transactions. PD itself is also composed of at least 3 nodes and has high availability capabilities. We recommend that you deploy an odd number of PD nodes. The TiDB server, this is the component I mentioned previously. It is responsible for handling client connections. In other words, when you connect to TiDB, the database, your client will connect to TiDB Server, the component. The TiDB Server is responsible for client connections, parsing SQL statements, compiling SQL statements, generating execution plans, and returning results to the client application. Execution plans are the steps the database will take in order to satisfy the query. You may be asking yourself, where does TiDB store its data? That's a great question. The OLTP data is stored in the TiKV cluster in the form of key value pairs. The TiKV cluster is responsible for data persistence, concurrency control, filtering data at the storage level so that queries run fast, high availability, and ensuring that the data is consistent. We will discuss how this is done in the TiKV module. The TiDB server layer is stateless. In practice, we will run multiple TiDB server instances. Each of these instances will have its own IP address that users can use to connect to. But this isn't how we do it in practice. We want to provide a single IP address to the outside world through a load balancer, such as LVS, HA proxy, or F5. Using a load balancer ensures that the client connections can be evenly distributed across multiple TiDB server instances. TiFlash is a columnar storage engine that provides the OLAP capabilities to TiDB. TiKV is the primary target for the data. TiKV will synchronize its data with TiFlash using the Raft consensus algorithm. This ensures load balancing and strong consistent reads. TiFlash also supports real-time updates. The combination of TiKV and TiFlash is what makes TiDB an HTAP database. Next, we will discuss the main functions, implementation principles, and features of TiDB, TiKV, TiFlash, and PD. Let's take a detailed look at the main functions and implementation principles of TiDB Server. TiDB Server itself is only responsible for the SQL computing engine and does not store data, so TiDB Server is stateless. When our system faces a large number of concurrent connections, we can load balance by adding TiDB server instances to improve high concurrency processing capabilities. The first thing we need to look at is 1. Handling client connections. Users are authenticated by username and password, and the connected users are empowered. That means that they can query the database. These tasks are mainly done by the protocol layer module. Number 2 is parse and compile SQL statements. After listening to the SQL statement, TiDB Server parses and compiles it. During the compilation process, it optimizes and generates an execution plan. These tasks are done by the parse and compile modules. Relational and KV data transformation. Since data is stored on TiKV in the form of key-value pairs, there's a big difference between relational database tables, which have tables, indexes, and rows, and a key-value pair structure. If you want to execute SQL, you must be able to convert between relational data and KV storage. Next, SQL statement execution. According to the compiled execution plan, it is executed on TiKV in batches. The data is read by the executor module and the dist SQL module, and the transaction-related operations are completed by the transaction module and the KV module. Execution of online DDL. The TiDB database is designed so that data definition language operations do not lock tables. This is done by the schema load module, the worker module, and the start job module. And finally, garbage collection. The garbage collection backend module is responsible for recovering data from old versions that have expired, and this part will be explained in the TiKV course. Next, let's take a look at the TiKV module. We have mentioned TiKV a number of times. It handles storing our relational data, that is, OLTP data. Persistent data. TiKV provides the TiDB database with persistent relational storage. To make this happen, PingCap chose the RocksDB storage engine. RocksDB is based on the LSM tree data structure. RocksDB is the persistent storage engine for TiKV. The RocksDB engine uses mechanisms such as write-ahead logs to ensure that data is not lost. Next bullet, distributed transaction support. TiDB uses a two-phase commit approach that is based on the Percolator transaction model published by Google. The Percolator transaction model ensures that storage lock space is allocated separately on each KV node. This uses RocksDB column family locks. This is also called a column cluster. The timestamp oracle and the PD also play a part in this process. The TiDB database supports two locking modes, optimistic locking and pessimistic locking. Next bullet, strong consistency and high availability of replicas. In the raft algorithm, data is stored in regions. Each region has 3 replicas. By default, a replica cannot be larger than 96 megabytes. If a replica exceeds this size, it is split into multiple regions. This helps ensure that TiDB can scale dynamically. Next is MVCC, or multi-version concurrency control. MVCC is essential for highly concurrent reads and writes. It is the basis for functions such as concurrency control, snapshot isolation level, distributed transactions, and fast data recovery. TiKV's MVCC implementation is done by adding a version number after the key, and after the historical version data reaches a certain period of time, it is cleaned up by TiDB Server garbage collection. Next up, coprocessor. This is really operator pushdown. The coprocessor function enables TiKV to perform data filtering, partial aggregations, etc. on the local node so that the SQL calculation can be pushed down to the distributed storage nodes to complete it. This mechanism not only reduces network interaction cost, but also makes full use of the computing resources, CPU, cache, and memory, of the TiDB server, and also makes full use of the distributed storage node's parallel processing power. Next up, we're going to talk about the placement driver. Do you remember the placement driver? We mentioned it earlier. It's most commonly referred to as the PD. It is the brains of the TiDB database. The PD is responsible for metadata storage for the entire TiKV cluster. The PD is responsible for maintaining where data lives on the TiDB cluster. It is responsible for maintaining information used by Raft as well. TiDB servers obtain routing information from the PD and then use that information to access data in the TiKV cluster. In addition, topological label information is stored in the PD. We will cover this in an upcoming module. I previously made a recommendation regarding the PD. Do you remember what it was? I'm going to make an uncomfortable pause here. That was uncomfortable. The recommendation was there should be an odd number of PD nodes in the PD cluster. We'll cover why that is in an upcoming module. Next, the PD is responsible for assigning a global ID and a transaction ID. The global ID we use, such as store ID, region ID, peer ID, table ID, index ID, etc., and the transaction ID of the distributed transactions are also assigned by the PD. The PD is responsible for generating a global timestamp using the timestamp oracle. Timestamp oracle is a global timestamp used to guarantee the order of transactions in the database. It's very important for the database to know the exact order of transactions in case we have to roll things back. We will introduce the details later. The PD is responsible for collecting cluster information for scheduling. The TiKV node periodically reports the status of the cluster to PD. The PD is responsible for scheduling the region among TiKV nodes according to relevant status. This has to do with what we talked about, splitting replicas and 96 megabytes, etc. in the previous section. We will introduce the details of this later. And finally, the PD is responsible for providing TiDB dashboard service. The PD hosts a small web server that runs the TiDB dashboard. The dashboard provides a place where you can easily find information about your TiDB database. Once again, we will discuss this later as well. The second component in our storage story is TiFlash. Recall that TiFlash implements the analytics side of HTAP. This is a good time to mention that TiKV, as the OLTP side of storage, is required. PingCap has customers whose use cases don't require analytics. These customers only use TiKV for their storage. If, really when, they decide they need enhanced analytics capabilities, they can easily install TiFlash, thereby adding OLAP capabilities to their TiDB environment. Here are some capabilities which make TiFlash special. Asynchronous replication. TiKV is the primary storage component. In fact, TiFlash cannot work without it. Another way to say this, I can have a TiDB database with only TiKV, but I can't have one with only TiFlash. When you insert, update, or load data into TiDB, it is written to TiKV first, then replicated to TiFlash. This operation is performed asynchronously. There is even a special Raft role that performs this task. The Raft learner handles this. If a TiFlash node goes down, or if the network has high latency, the data can be read from TiKV. This redundancy ensures normal operations. This replication mechanism also inherits the automatic load balancing and high availability of the TiKV system. It does not rely on additional replication pipelines, but directly receives TiKV data transmissions in a one-to-many manner. As long as the data in TiKV is not lost, a replica of TiFlash can be created at any time. Next, consistency. TiFlash provides the same snapshot isolation level support as TiKV. This ensures that the read data is up to date, and that is, ensuring that previously written data can be read. This consistency is achieved by verifying the replication progress of the data. Each time a read request is received, the region replica in TiFlash initiates a progress check, a very light procedure call request, to the leader node. and only responds to reads if the process ensures that it contains at least the data covered by the read request timestamp. Next, number 3, or the third one. Column-oriented store improves analytics query efficiency. Yeah, we've said this before, but it's worth repeating. TiFlash is a columnar data store. Columnar data stores were designed for analytics workflows. Row-based storage is best used for transactional processing. So row-based storage is ideal for use cases involving indexes and small resultant sets. Columnar storage is ideal for use cases involving table scans and analytics techniques that require reading the data multiple times. The introduction of MPP, or massively parallel processing functional architecture, distributes computing tasks to multiple server nodes in parallel. After the calculation is completed on each node, the results of each part are summarized together to obtain the final answer. This processing model makes the analysis query service on TiFlash more efficient. Next, business isolation. This is a good one. As mentioned earlier, the column store is very friendly to statistical analysis queries, or OLAP, and the row store is friendly to transaction, OLTP. So TiKV and TiFlash can be used for 2 distinct business scenarios or use cases, OLTP and OLAP. Using one environment for both of these use cases saves admin and processing cost. Plus, and this is huge, it means that you don't need to create and manage OLTP to OLAP ETL processes, thus saving more time and resources. And finally, this one's my favorite. Whether it's TiKV or TiFlash, their SQL entry is the TiDB server. So what does that mean? This means that your queries for both sides go through TiDB Server, and the optimizer in TiDB Server can choose between TiKV and TiFlash based on the query. So this is based on the SQL statement. So as a DBA or developer, you write the query and TiDB chooses the best place to go for the data. You don't have to worry about it. Totally transparent to you. This marks the end of the first module. We've taken a brief look at TiDB and its architecture, so you can now describe the overall architecture of the TiDB database. And you understand, well, understand isn't really a goal. Let's say you can describe the main functions of TiDB Server, TiKV, and the placement driver. Can you describe the difference between TiDB database and TiDB Server? TiDB database refers to the entire database environment. TiDB Server, on the other hand, refers to the SQL processing component of the TiDB database. So TiDB Server is a component of TiDB database. Thank you for taking the time to view this module. We hope you enjoyed it and learned a great deal.